This is lecture 20. In this lecture, we will review acid-base chemistry, and we'll talk about it in terms of the general chemistry level. The objectives for this presentation are the review of basic acid-base theory, simple acid-base equilibrium calculations. So, our simple theory, definitions of acids and bases. The original definition that we learned at the general chemistry level was the Arrhenius definition. An acid makes hydronium ions in solution. That's the modern way of saying it. Arrhenius actually said hydrogen ions were made in solution. We realize that hydrogen ions don't actually exist. They're always in the form where they're protonated water, so it's hydronium. Is the proper form, but frequently we will write it as H+ because it is a convenient shorthand. Bases produce hydroxides in aqueous solution. Right? Lewis came along and was interested not only in defining acids and bases in solution, but in many other circumstances, including organic chemistry. And acids are electron pair acceptors and bases are electron pair donors. Right, so the vast majority of organic chemistry reactions are Lewis acid-base reactions of one type or another. And finally, we have Bronsted-Lowry theory, the modern theory of acids and bases that is used. Acids are proton donors and bases are proton acceptors. Let's look at Bronsted-Lowry theory because that's the one that we use most extensively when we talk about acid-base theory today. And acids and bases exist as conjugate pairs, and that pair is connected by the transfer of a hydrogen ion, a proton. The proton never exists free in solution. It is transferred through a collision. So in this case, HCl collides with water, and HCl loses a proton, a hydrogen ion, to water, forming hydronium, and what's left is chloride. So we have a hydrochloric acid molecule, and it is forming a it's losing a proton to make hydronium, and its conjugate base is chloride. So that's an acid-base pair, right? So water's acting like a base because it's absorbing a proton, it's attracting or accepting a proton, and HCl is the acid in the reaction because it's the proton donor. And its conjugate base is chloride, and the conjugate acid for the base water is hydronium ion. Acids and bases appear on opposite sides of the chemical reaction as acid-base conjugate pairs. The same thing happens with bases, right? In this system, when we look at our ammonia collides with water, and in this instance, the water is now acting like an acid. It's donating the proton and becoming hydroxide. So water's the acid, and hydroxide is its conjugate base, and ammonia is acting like a base, and its conjugate acid would be the ammonium ion. Okay, conjugate pairs. Properties of water. Water acts both as an acid and a base. With HCl, it acts like a base. With ammonia, it acted like an acid. It's both an acid and a base. That's amphiprotic or amphoteric. Both are used. Amphiprotic, meaning like an amphibian that lives on land and water and in water. Amphiprotic means it can both gain and lose protons. That means that it can react with itself, and this is an equilibrium. Two waters can make a hydronium and a hydroxide. Water can react, right? And this process is called autoionization, and there's an equilibrium constant for that autoionization, Kw. Notice once again, water is the solvent, so it doesn't appear in the equilibrium expression that goes with the balanced chemical equilibrium. Right? Kw at room temperature is 1.00 times 10 to the minus 14th. That's our autoionization constant for water. That's one of the few constants that you're usually expected to know. It's kind of like knowing Avogadro's number in first semester chemistry and second semester, you're expected to know what Kw is. Let's calculate the equilibrium concentrations of hydronium and hydroxide in pure water. Just like we did in general equilibrium before, the first thing we need to do is write the balanced chemical equation. That's already written in front of you. We're going to fill out the reaction table. Right? We don't have to worry about the amounts, right? The amounts of water, because water is our solvent. And remember, in our equilibrium expression, the Kw in this case, water doesn't show up because it's the solvent, so we don't have to worry about the amount. We would if we were actually doing a more sophisticated calculation. Notice that we would have to lose 2 times as much water as hydronium and hydroxide that we make. At equilibrium, we're only going to have the hydronium and hydroxide in solution to worry about. We write our equilibrium expression. We plug in the values for hydronium and hydroxide from our reaction table. We plug in the value for Kw, which is 1.00 times 10 to the minus 7th. And then we solve for x, which means we just take the square root of both sides. We know the concentration has to be positive, so we're going to take the positive root. Right? The negative root would be a negative concentration, which is a non-physical answer. And so we find at equilibrium, the concentration of both hydronium and hydroxide are 1 times 10 to the minus 7th. And then we can add back the fact we know concentrations are in molars. Because remember, they're actually activities, but we're stripping off the molarity by dividing by the standard concentration, which is 1 molar. Okay. So hydronium and hydroxide were equal to each other. Just a reminder about the pH scale. How do we measure how much or how acidic or how basic a solution is? We usually use the pH scale to do that. And it's a logarithmic scale because we have so many orders of magnitude of different concentration of hydronium and hydroxide in solution that we use that logarithmic relationship. And so we compress the scale with the logarithm, and it is, since it was originated with analytical chemists, it will be a base 10 logarithm. So the pH is the negative log of the hydronium ion's activity. And of course, at this point, instead of using activities, we substitute the concentration with the units removed because it's concentration divided by C standard. So we just drop the molars. That means on our scale that we have, starting at a pH of 1, which is a 10th molar hydronium concentration. We also have then the hydroxide and hydronium have to multiply to 10 to the minus 14th. So that tells us that our concentration of hydroxide is 10 to the minus 13th. And that means the pOH is 10 to the minus, is 13.00. And as we step down by powers of 10 each time, the pH goes up by a power, by adding 1, because it's a logarithmic scale. It's the negative of the exponent in these ones that have 1 out front, concentrations with 1 out front. Once we reach the concentration where the acid and base is equal, that's our neutral pH, and the pH and the pOH equals 7 in a neutral solution at room temperature. We can continue in the basic direction, and we go all the way down to 10 to the minus 13th molar hydronium, which corresponds to 10th molar hydroxide. There are occasionally concentrations higher than 10th molar in natural environments, and very, very rarely they would be below. They would be higher than 10th molar for hydroxide. So we could see things that approach a pH or pOH of 0. Now, weak acids, right? We have 7 strong acids which are 100% ionized: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, chloric, and perchloric, right? If they're not those 7, then they're not a strong acid. They're weak acids. They don't ionize 100%. So express the ionization as an equilibrium. We write the Bronsted-Lowry exchange of a proton with water, right? So our weak acid will be symbolized as Ha, and there is no A on the periodic chart by itself. So that's just meaning HA is the protonated form of our weak acid and A minus is the deprotonated form. HA protonates water, and the conjugate acid of water being a base is hydronium, and the conjugate base of HA being an acid, its conjugate base is A minus. Right? And so we can write an equilibrium expression for this, just like we did for water. Notice, once again, water is the solvent, so it doesn't show up. So our products are hydronium and A minus, and the HA will show up in the bottom of the equilibrium expression. And we call that equilibrium expression, the constant that goes with it is the acid ionization constant, K sub A. And so there's our K sub A for a weak acid. How do we look at the strengths of weak acids? The nice thing that happens about acids is every acid-base reaction is a single step, which is a 1-to-1-to-1-to-1 chemical equation. They're all of the same basic form. If it's a weak acid, it makes hydronium and its conjugate base. It makes hydronium and its conjugate base. Now, Kas all then have exactly the same form. What that means for us then is if we compare the sizes of Ka, we can determine the relative strengths of weak acids. The larger Ka is, the stronger the acid. All right, so let's compare some weak acids. We have acetic acid. Its Ka is 1.8 times 10 to the minus 5. We have benzoic acid, whose Ka is 6.3 times 10 to the minus 5. We have hydrofluoric acid, whose Ka is 1.9 times 10 to the minus 4. And we have formic acid, whose 1.8 times 10 to the minus 4. If we want to determine which one of these acids is the strongest, right, we would have to look for the largest Ka. And if we were looking for the weakest, we would have to look for the smallest Ka. So if we were going to rank these, first of all, the largest in this entire group would be hydrofluoric. And the smallest, or fourth place, is going to be acetic. And the next one after hydrofluoric would be formic, and benzoic acid would fall in between. Okay, so we got the ranking exactly as we ordered them. Let's look at why acids are acidic and other compounds that contain hydrogen atoms are not. Specifically, we're going to compare acetic acid, which is also known as ethanoic acid, is its IUPAC name, because it has 2 carbons in it. We're going to compare it to ethanol, which is an alcohol with 2 carbons. Why is the acetic acid going to be acidic and ethanol is not. Right? So we're going to first draw their Lewis diagrams and compare them. There's our Lewis diagram for ethanol. There's our Lewis diagram for acetic acid. What happens when we place a carbonyl right next to our alcohol group, our OH group, COH group? That's an electron withdrawing group, right? Oxygen's extremely electronegative. So it's going to pull electron density towards it. So that weakens the bond. That makes that proton much more easy to remove. It's already got a fairly weak, highly polarized bond because oxygen is 3.5 on the electronegativity scale, and hydrogen is 2.1. So let's look at the conjugate bases. That's going to tell us even more. There's ethoxide. That's an extremely strong base. And there's acetate ion, right? Ethoxide being a really strong base means it's highly reactive. It really wants that proton back, and it's not a particularly stable form. What's special about our acetate ion? Well, that's not the only form we should draw it in. It has a resonance structure. Okay? And with that resonance structure, that increases the stability. We have resonance, and that means increased stability. If the conjugate base is stabilized, then it's more likely to form. That makes the acid form more likely to donate its proton. So now we're going to do an example of calculating the pH of a weak acid. Right? Our example is going to be for 10th molar acetic acid. So we'll start off by writing the balanced chemical equation for the ionization of acetic acid, and then we'll start filling in the reaction table. Since the label that's actually used for the concentration of our acetic acid is our analytical concentration, that means as made up, not what's actually in the solution. Then when it says 10th molar, it simply means if there's a liter in the container that 1/10 of a mole was added to that to make a liter of solution. All right. We know that it's not all acetic acid. Part of it's ionized to make acetate. It's just that a small amount of it is ionized because it's a weak acid. So that means that we start off with a little thought experiment. We're going to start off as though all of the acid is still in its protonated form. So there's no acetate in solution and no hydronium. Then we fill in our reaction table just as we did in the previous lectures. We are going to subtract, because it's a reactant, so it has to disappear. And the stoichiometry is 1, so we subtract an X. The stoichiometry for acid-base reactions is 1 to 1 to 1 to 1, which makes things very simple. Don't have to worry about the concentration of water. It's the solvent. we are going to add x, because once we cross the equilibrium, what disappeared was reactants. We're now looking at products. Products up here, so they got positive signs. Now we add before and change, and that gives me the equilibrium concentration. So we've got 10th molar minus x, x and x. We then write the equilibrium expression and plug the values in, and we end up with the Ka for acetic acid is 1.8 times 10 to the minus 5. That's going to equal x squared divided by 0.1 minus x. If we unwind that, we're going to end up with a quadratic, and we can solve it using the quadratic equation. I don't know about you all, but I hate quadratic equations. They're such a pain to solve. It usually takes me a couple of goes before I get an answer that actually makes sense. I usually drop a negative somewhere along the line, so we can find approximate answers that'll work reasonably well. And reasonably well in general chemistry was about 5%. So let's make some approximations. We'll make a single approximation. It's called the small x approximation. Since we know x is going to be small because that's the amount of conjugate base being made, and this is a weak acid, so it doesn't ionize completely. So x is going to be small compared to the analytical concentration. We can't ignore x's when they multiply. Multiplicative results, if x is small, x squared is even smaller, but that doesn't mean it's 0. But when we add and subtract, we can ignore x when we are adding or subtracting it with a larger number. And since 0.1 molar is our analytical concentration, we can assume safely that that's bigger than x. And so our 0.100 minus becomes 0.100. Our 0.100 minus x will become 0.10. Okay, so we make that approximation. Here's where we were on 2 slides ago. We make that approximation. Now we have a perfect square. When we bring the 10th molar across, now that's equal to x squared. We can take the square root of both sides, and of course we know that that's going to be the positive square root, and that gives me 1.3 times 10 to the minus 3. And from our reaction table before, x was both the concentration for our hydronium ion and for our acetate. So we know both concentrations. We also know that in reality, this is in molar. Let's calculate our value for the acetic acid that's left. So we would take 0.10 minus x from the reaction table. That gives me 0.10 minus 1.3 times 10 to the minus 3. That's 0.9997, but our addition rules tell us that's good in the thousandths. That's good in the 10,000ths place. We have to round back to the thousandths place. We got to round back to there, which means it becomes 0.100 still. It agrees within, better than 1. It agrees within 0 of its last significant digit, right? Double check. We plug it into the the Ka expression, right? So we get 1.3 times 10 to the minus 3 cubed. And it's squared, over 0.1. And that gives me 1.7 times 10 to the minus 5. I differ by 1 in the last significant digit of Ka. That's good enough for government work. That's a check. So now we take our negative log of 1.3 times 10 to the typo minus 3. 2 typos in the same slide. Equals 2.87. Sig fig rules for pHs and logarithms in general state that if we have 2 sig figs in the argument in our logarithm, we get 2 decimal places. That's 2 sig figs becomes 2 decimal places. If you do an anti-logarithm, the number of decimal places tells you the number of sig figs. Now, before we go on, we can also do this in a generic way. We can leave all of our symbols in. So here is the equilibrium expression, and the only symbol we haven't seen before is C0. That's the initial concentration or analytical concentration of our weak acid. And so when we did the small x and brought C0 to the left-hand side, that's equal to x squared. Take the positive square root of both sides. So x was the square root of Ka times C0. And we know that x is the hydronium and the acetate concentration. This is a toolkit way of calculating these quickly. In general chemistry, we wanted you to write equilibrium expressions and reaction tables and all the way through. Many times you need to do these calculations very rapidly, and consequently we have this situation where we can calculate it directly by remembering a simple formula, that hydronium and conjugate base are equal to the square root of the product of Ka times the analytical concentration of the acid. So, weak acids and weak bases, small x approximation. For weak acids, that's going to work. And that will give us that x is equal to A minus times is equal to hydronium is equal to the square root of Ka times the analytical concentration, C0 of the weak acid. For our weak bases, we'll get the same exact result, except that will be the protonated form of the base. It'll be a hydroxide concentration, and it will be Kb, the base ionization for the base, times C0. Now, of course, we have MathCAD to do the complete calculation, but how do we get the guess? We'll use these rules of thumb, right? These simple calculations to get our guesses for more advanced calculations later on. All right, what about polyprotic acids? We know that polyprotic acids have more than one acid site. Examples are carbonic acid, which is diprotic, phosphoric acid, which is triprotic, citric acid, which is a tricarboxylic acid, it's triprotic. And these multiple acid sites mean we have multiple Kas. Deprotonating one site affects the ability to be deprotonated in its neighboring sites. How can we predict the relative sizes of these Kas? Let's take a look at polyprotic acids now, or use as our example one of the simplest. This is carbonic acid. Carbonic acid is a dicarboxylic acid. Okay, there's our carboxylic acid group. We have a second carboxylic acid group, but they're sharing the same carbonyl. Now, what we're going to do is remove one of these protons. That's going to be our first ionization, right? It doesn't matter which proton you remove. It has the same Ka. The left proton or the right one will be similar lability, how labile, how easily removed they are. The second one, however, is going to be different. Since one's gone away, it's no longer symmetrical. It's no longer neutral. It's a negative ion. Okay, so that's going to affect. The two protons are identical, but there's a great difference between removing the first and the second. Turns out that there are 4 orders of magnitude difference between the two. 10,000 difference in the Kas. All right, so let's try to understand the difference in the size of these two Kas. Right? In the first ionization, we remove a proton. Remember, a proton is +1, and we're removing it from a -1 ion. The attractive force here is 1 times 1 divided by 4 pi epsilon 0 times the square of the distance between the two charges. What happens when we remove the second proton? We still have a positive charge, but now we have a -2 charge that we're separating it from. We're pulling it apart against twice as much force, which means we got to do a lot more work. It's going to take more energy. It's going to change the Gibbs energy of the process, which consequently means it's not as likely. Right? It should be at least twice as hard to remove that proton, which means it's going to be twice as hard to remove that proton, which means that Ka2 is going to be a lot larger than Ka1. Now, in many cases, Ka1 and Ka2 are different by more than a factor of 100. If that's true, we can treat them as two separate equilibria instead of having to work with them as linked equilibria. This allows us to approximate the hydronium ion concentration in solution by ignoring the second ionization and treating the material as though it were a monoprotic acid. So for instance, what's the pH of 10th molar carbonic acid? We set up the process exactly like we did for our acetic acid. We use the small x approximation, and we end up with x is equal to 2 times 10 to the minus 4. We take the negative log of that and gives us 3.69. Okay, now remember, x is going to give me both the concentrations of hydrogen carbonate and hydronium. Because we're going to ask another question. What happens with the second ionization? What's the concentration of carbonate that comes from the second ionization? So let's look at its expression. Well, we just calculated hydronium and hydrogen carbonate, and we said they were equal to each other, which means they cancel, which leaves us with the hydrogen carbonate concentration, the carbonate concentration, right, is equal to Ka2. This is generally true for polyprotic acids if we can make this approximation. If we can't make the approximation, we're going to solve it with MathCAD. And what do we need? Guesses. What's going to be a good guess using these approximations? So our approximate diprotic acid, right? The monodeprotonated form, the intermediate form, HA minus, is equal to the hydronium is equal to Ka, the square root of Ka1 times C naught, and the dideprotonated form, the ultimate conjugate base, second conjugate base, would be equal to Ka2. All right, so we've talked about acids and bases. What about the salts of acids and bases? Let's predict what we know about the salts of acids and bases. When an acid and a base react with one another, they neutralize each other and they form a salt and water. Right? This is a neutralization reaction. And what we want to determine is the acid-base properties of the salt. We can make this solution in two different manners. We can do what we just talked about here. We can react the two, right? So we're pouring 2 beakers of solutions together into another beaker. So we're pouring acid and base together and reacting them to make the salt solution, or we can start off with a beaker of water and we can add the solid salt to it. And if we make the concentrations the same, there's no way for you to know which way it was made. If I give you a solution of sodium acetate, how can you know if I made it by neutralizing sodium hydroxide and acetic acid, or if I dissolved sodium acetate in water? You can't. The chemical properties have to be the same. And this helps us because it's going to turn out to figure out what's going to happen. We're going to want to use the neutralization reaction, but when we have to calculate how much, it's going to be better to dissolve the solid. Okay, we're going to pick those. So let's look at what happens when we do a neutralization reaction between our four possibilities. We have strong acids and strong bases. So we can have a strong acid, right, reacting with a strong base. We can have a strong acid. Acids are across the top. Bases are going down. A strong acid with a weak base. We can have a weak acid with a strong base and a weak base with a strong base. We've got four categories to fill in. So let's look at an example. Strong acid, strong base. Who's stronger? They're both strong. They're both ionized 100% in solution, so they're equally strong. That makes it a tie, right? That means the salt is neutral. This is a neutral salt. So when we start filling in our table, we now put in strong, strong gives us a neutral solution, pH 7 for the solution. Right? What happens if we now substitute a weak acid for the strong acid? Now we have a strong base with a weak acid. That makes sodium fluoride salt and water when we mix them in equimolar amounts. That's a strong base plus a weak acid. Who wins? Well, the base is stronger this time. So the base wins out over the acid. That makes it a basic salt, which means when we have strong base, weak acid, basic salt. Let's do the reverse. Substitute not for the hydrochloric acid. Now we're going to substitute for the sodium hydroxide in our first reaction. We'll use a weak base. We'll use ammonia, meaning we make ammonium chloride. All right, so we've got our ammonium chloride solution. Okay, so acidic or basic? Well, we have a weak base, strong acid. Who wins? The acid is stronger than the base. It's an acidic salt. What happens if they're both weak? How can we figure out who's the stronger acid and the stronger base? How do we measure the strengths of acids and bases? How did we rank relative strengths of acids a few slides ago? We looked at their Kas. How do we rank the strengths of bases? We rank them according to the larger the Ka, the stronger the acid. The larger the Kb, the stronger the base. Right? So what we have to do is compare the Ka of the acid to the Kb of the base. Okay. The example I just chose is a very rare circumstance. The two Ka and Kb are both the same. Matter of fact, this is why most general chemistry people choose this. We only have to remember one K value because both ammonia and acetic acid have the K value. The difference is acetic acid is a Ka and ammonia's is a Kb. That means this is a neutral solution. But if I had used benzoic acid instead, benzoic acid is a stronger acid than acetic acid. We'd have ammonium benzoate would be an acidic salt because benzoic acid is stronger than ammonia. Okay, so now we've got our table that helps us to predict. How do we calculate those values? And what we have to do is look at the relative values of the Ka of an acid to the Kb of its conjugate base, or the Kb of a base to the Ka of its conjugate acid. The stronger the weak acid, the weaker the conjugate base, and vice versa. The weakest acid we looked at so far was ethanol. And we said ethanol is essentially not acidic in aqueous solution. But then we talked about the ethoxide ion, its conjugate base, and said it was hugely basic, right? The weaker the acid, the stronger the conjugate base. That happens in all of these, all right? So there's got to be a relationship between the Ka of the acid and the Kb of the base, and it turns out the two multiply to give us Kw. So we can apply that. We can apply that to the pH of salts. We've got sodium acetate here. How did we make that sodium acetate salt? Right? It's sodium hydroxide and acetic acid. A strong base, a weak acid, it's a basic salt. Who makes that solution basic? The sodium comes from sodium hydroxide, and the acetate comes from acetic acid. And what's left over is our water. Okay. If acetic acid is a weak acid, then acetate is a weak base. If sodium hydroxide is a really, really strong base, then sodium ion is a really, really, really weak acid. It's so weak that it's a spectator ion. Okay, basic salt. Right? Sodium is the conjugate acid of sodium hydroxide. It's a spectator ion. We don't have to worry about it in our equilibrium. The equilibrium is going to be acetate with water. And the product of acetate reacting with water is going to be acetic acid and hydroxide. That's what makes it basic. Arrhenius tells us basic materials make hydroxide an aqueous solution. Okay, so there is our base ionization, or the base ionization reaction for acetate. How do we find the Kb for acetate? We have to use our expression that relates Kb to Ka. Their product was Kw. To get a Kb from a Ka, you have to divide Ka into Kw. To get a Ka from a Kb, you've got to divide Kb into Kw. Either direction. Here we needed a Kb, so we're dividing Ka into Kw, and we find out that, acetic acid is a middling strength weak acid, so we're going to end up with a pretty weak base. The stronger the weak acid, the weaker its weak base. So, right, look at that difference. So that's going to make it a pretty weak base, which makes this calculation pretty exact for small x because it's much less ionized than the acetic acid would have been earlier. And we find out when we get to using our rule of thumb equation that x is equal to the square root of C naught, which is 0.1, times Kb, which is 5.6 times 10 to the minus 10th, that gives us 7.5 times 10 to the minus 6th, which is equal to the amount of conjugate acid produced, acetic acid, and the hydroxide produced. So if we take the negative log of that, we get 5.12. That is not our answer. If that were the pH, that would mean it was acidic, and we predicted a basic salt. That's not the pH, that's the pOH, so we have to subtract it from pKw, and that gives us a basic pH of 8.87. So finally, we come to our last topic from general chemistry, and that is solutions containing both acids and conjugate bases. So what happens if I take sodium acetate and I add it to acetic acid? Well, we know we have a pure acetic acid solution. We're adding a basic salt to it. We just calculated that it was in a basic salt when it's dissolved in water. So we're going to add that basic salt to an acidic solution. It has to become less acidic. But it's also a common ion. Acetate is the conjugate base of acetic acid. So this is a common ion process. I've got two different reactions. I have the equilibrium of acetic acid with water to make acetate and hydronium ion. And when I dissolve in it solid sodium acetate, I produce acetate ion and sodium, which again I ignore because sodium is a spectator ion. It has no effect on pH because it's the conjugate acid of the strong base sodium hydroxide, which means it's negligibly acidic. Okay, that leaves us with acetate ion in common between the two. And what's Le Chatelier's principle tell us? You add a product, it's going to shift back towards reactant. When it does that, it also has to consume the hydronium ion, so the hydronium concentration goes down. It's less acidic, just like we predicted. But now, I've predicted what happened. That's the common ion effect, right? I've predicted what happened. Now we got to calculate it. Now we're going to have two concentrations to worry about. We've got substantial amounts of the acid form, and we've got a substantial amount of the base form. And if I add a little bit of acid, these two numbers aren't going to change very much. If I subtract some of the acid, these two numbers aren't going to change very much. In other words, the pH isn't going to change. If these two don't change, then the hydronium, when it returns to equilibrium, it'll be at nearly the same hydronium concentration it was beforehand. It's resisting the change in the pH. So the addition of acid would temporarily increase the hydronium, but it would shift back to equilibrium, and it would return to approximately the same pH. We call things that are pH resistive to change buffer solutions. This is a buffer. It's an acid mixed with its conjugate base, or a base mixed with its conjugate acid. Right? So we use Ca for the concentration of the conjugate acid, Cb for the conjugate base form, and we do equilibrium calculation. This time we start off with Ca of the acid and Cb of the base. Add X to the Ca, we add X to the Cb, we subtract X from Ca because it's a reactant, it's disappearing. We add X to Cb because it's a product, it's appearing, and we get X more of hydronium ion. So at equilibrium we have Ca minus X, Cb plus X, and X. We plug that in now into our equilibrium expression, right? And then we apply the small x approximation. Only we can now apply it twice, because if you add X to Cb, right, if it were just the weak acid calculation, we'd be worried. But remember, we're even less acidic than we were for the weak acid. Surely we can ignore it when we're talking about its buffer, where it's been made less acidic. X is going to be smaller. So both of these can be ignored. And so the only X we get is the one that corresponds to the hydronium ion concentration. We take the negative log of both sides. We bring the Cb over Ca log across to the opposite side. When we do that, it changes sign, and we end up with the pH of the solution is equal to the pKa plus the log of Cb over Ca, better known as the Henderson-Hasselbalch equation. That's our buffer equation. So now we know how to calculate the pH of buffers, right? Now, rules for using the buffer equation. In order for X to be small in this solution, we have to have a relative concentration of Cb to Ca that's between 0.1 and 10. If it's outside of that range, which is one pH range, one pH unit on either side of pKa, then it's not going to be a buffer once it gets out of there. In that other range, between a tenth and a 10, we'll get a slow change in the pH of the solution with the addition of acid or base. This ends what we have to talk about the general chemistry work. Right, next time we're going to be looking at the section in the textbook that corresponds to 5F. That looks at more complicated acid-base equilibrium. In particular, we'll be looking at polyprotic species and looking at the salts of polyprotic species, which are more complicated to calculate.